Well, I still haven't uploaded the recordings from the other day, so I'll do that today as well. Maybe when you guys are in your breakout rooms, I'll start uploading stuff. Okay. So now we're recording. Share screen. Great. So, yeah, you with that mass have just come down ski slope and are traveling 18 meters per second using a slide on a flat terrain, being slowed by frictional forces. Okay. It takes 7.3 seconds for you to come to a stop. Okay. Draw a skill diagram showing that all forces acting on a slide. Calculate the value of acceleration, also turn using variables, how sources connected, calculate distance. You think you'd want to know yeah, this one's actually not using any forces, I guess. I don't think so. Okay, so let's draw this. So do copy what I have here. And you're traveling 18 meters per second. Your weight 75 kilograms. So we do know that we are coming to also flat terrain. We just came down a ski slope. Got it. Duh. Sorry about that. Okay. So you got to read carefully. Okay. So here's a ski slope. So now you're here. That's what we got to read carefully. That's important. Because otherwise, you notice I was kind of lost there. Good. So here's the deal. Our initial velocity is 18. Our final velocity is going to be 0. Our time is 7.3. But in terms of this, the only thing we're really interested in is, of course, our normal force, weight due to gravity, and of course, F net. So that's our free body diagram. I know you guys haven't had much practice, so I'm not going to ask you to do it on our test. Don't worry. I'll give you diagrams for problems like this. But now we go to part B. We calculate the value of the acceleration, which would go down here. Remember, our x minus x0. I also determine using variables how the acceleration is connected. Coefficients. Okay. So, yeah. So what you want to do is you want to use this. We don't care for that's irrelevant. But A we don't know. So remember what A equals. Then also keep in mind that you are coming to a stop. So once you get your acceleration, so reason why we could, and actually you see that also, FK. So I forgot to write FK as well for part A, because you do have friction, obviously. So F net minus FK is going to equal 0. Because you stop. So if I focus on that formula, remember F net's M times A. That's going to be mu K times M times G. Because remember, mu K is, FK. Our null force is going to equal weight, which is, of course, mg. So actually, the m's just cancel. That kind of makes your life a little easier. And once you get A, you can just throw that in and solve for mu k. And then calculate distance to side before coming to a stop. You can, once you have your acceleration, you can use your A value, V and V0, and solve for that. Remember, the formula for that one's going to be so. I've given you the equations that you'll need to use.
Mr. Washington, how did you get the MA or mass times acceleration equals mu k time?
Right. Yeah, and I know that's the part that's been the biggest pain point here. The reason why I'm saying equal to each other is that this is coming to a stop. So your acceleration is going to be negative. So eventually you're going to be motionless. So ultimately, your I don't want to say your net force is. There is a net force slowing you down. Put it this way: the net force has to balance out with the kinetic friction.
I'm just confused on how you got from F net minus FK equals 0 to MA equals MK times MG.
Oh, F net's MA.
F net's MA.
Yeah, let me do this. Let me redo it. Let's just erase all this here. So F net minus Fk is going to equal 0. So the only two forces acting on the skier is the kinetic friction and the force slowing that person down. So the force slowing the person down is basically the same thing as the kinetic friction because kinetic friction is slowing the person down. So you're deliberately setting these equal to each other because they both, because that minus that's going to equal 0 because they are going to balance out. And F net's MA and FK is this. And the ends cancel and you just solve for UK. So one way you could think about it is that how's a person going to stop because of friction, right? And so that has to equal your mass times acceleration.
Mr. Amashine?
Yep.
Would we have to do this on the test? Would we have to be able to do this?
Well, yeah, you definitely have to know this stuff here. And
well, yeah, with the F net minus FK and then
yes, this scenario I think is a little bit more challenging because it's kind of hard to tell. I think something that we did with the sled or the or pulling the sled, I think something like that might be a little more reasonable. I think because you guys are having a hard time understanding how these balance out. It's kind of a different scenario. I would say I'd probably be more in favor of this one. Let me go back here again. Problem sets. Problems like these here, where actually you do know what the net force is, and then you can break it down by its components, and so you're kind of doing a balancing act. Put it this way: this guy right here, right, the skier, we had to figure out his acceleration. So our F net. Well, let me make sure you guys. Let me go back to the previous screen first. You You guys have all this information down? Yeah, okay. So you're gonna be using this to do this with your partner, for your lab group. Going back to this one here again. Remember, this is weight parallel and FK. Overall, the net force is the difference between those two. And the net force, of course, is just M times A. And this right here, remember, we said was mg times sine theta, and that was mu k times Fn. Remember, Fn was mg cos theta. And then we worked it all out, right? Going back to, and remember, Fnet's always MA. And what are the forces you have here? Just those two forces, right? But they're going against each other, which is why it's subtracting. Now, going back to the lab again, really what's happening here, and I think maybe maybe I don't draw Fnet in the diagram. I think maybe that's what's confusing you guys. So you have the slope, right? He's now on this flat ground. What's truly the only force acting on him? It's FK, right? But what direction is he moving in? Moving to the right. So your F net is simply going to be, you can think of as negative FK if you want to call it that. So mass times acceleration equals negative mu k times mg, and you keep the g positive in this case because you kind of know that your acceleration is going to be negative because it's slowing you down, and you have the negative taken care of over here. So it's negative mu k times 9.8. But of course, you have to solve for acceleration from this information here and coming the rest. So really, just see what forces are acting on it and call it Fnet. That's what you're doing. And Fnet's always MA. So yes, I am going to ask on the test, but maybe I'll do it where it's a little more obvious. Like maybe when you have more than one force acting on it, I think that might make it easier for you guys. Like, W parallel minus FK equal to Fnet. Or here, F applied in the parallel direction minus FK equal to Fnet. So we'll do more of these. Actually, let's do the second question of the lab. Let me get that set up, and hopefully that will help you guys out. And it looks like there was a question in the chats? Okay, so great question. So someone asked, what's the difference between Fnet and Fn? Fn's a normal force. Okay, so Fnet, let's go back again to the screen. Let me share. Okay, so Fn is purely perpendicular to the surface. Fnet is parallel to the surface. That's the main difference. And Fnet is the overall force the body experiences, or the object, we'll just call it that, while in motion. So that's how you think of it. So let me set up two for you guys now. I'll put you guys in groups. Young parents dragging a kid that weight, okay, across the snow flat ground. That means the rope attached to the sled. The rope makes an angle of 30 degrees with respect to the ground. The tension of the rope is 160 newtons. So that's applied force, by the way. So yes, we're doing tension today. That's just applied force. Does mean a constant velocity of 1.5 meters per second. So you have the ground. You have your sled here. So this is your applied force. Or actually, let's just call it T, since we're calling it tension. It'll be Tx and Ty. And so Tx is going to the right, Ty is going up. And of course, we know that we have Fn. Oops, hold on. You have weight. And we also have Fk. So your net force, just so you know, is going to be Tx minus Fk. Or Ma equals Tx minus Fk. Hopefully that makes sense, what Fnet is representing now. Because where's my motion? My motion is horizontal. And what are the horizontal forces? Tx and Fk. Are they opposite directions? Absolutely. Subtract them. Hopefully that clears that up. Fn, of course, is a vertical force, right? Now here's the deal. For my perpendicular forces, perpendicular to the surface, what are all the perpendicular forces here acting on the sled? Or all the vertical forces, we'll put it that way.
Weight.
What else?
Normal force.
And Ty, and tension in the y direction. So Fn plus Ty minus W, what must all that equal?
0.
Exactly. Because there's no vertical motion. You're not going to set it equal to Ma because you're not moving up or down. So that's how they balance out. So to calculate it, obviously we'll leave Fn as is. Remember Ty. Ty is going to be T, and your angle's right here, obviously. That's going to be T times cosine, no, sorry, sine. My bad. And Tx will be T times cosine theta. So you're using that also. And the tension you already know is 160, so that's easy. 160 times sine 30 degrees. And then the weight is the mass times gravity, so 65 times 9.8. So you're going to be able to get Fn just fine. And you don't need to make the G negative because the negative is already taken care of over here. So you don't have to do another negative in that regard. Once you have that, calculate the force of friction acting on the system. Remember, Fk is mu k times Fn. So you're good there. Now sometimes Fn equals mg. That's when that's the only two vertical forces. If you have just Fn and W and that's it, you don't have this Ty, then of course Fn equals mg. But that's not true here because you had a third force, you had Ty. So keep in mind, Fn does not necessarily equal mg the whole time. That's really messy. does not necessarily equal mg the whole time. The only time it would is if those are the only two forces, Fn and mg. That's it. If you're pulling something straight up horizontally, like you're pulling something at 0 degrees with the horizontal, with the ground, then yes, Fn equals mg, absolutely. Because you got no other vertical forces going on there. But because we have another vertical, because you're pulling something at an angle, which has a vertical and a horizontal component, now you got a third vertical force you got to take into consideration, which is that Ty. So C, you're just going to do that. You'll calculate that. And then for D, oh, wait one sec. Sorry, they don't give us mu k. So C, my bad. I didn't read that carefully. For C, we're using this equation. We can't do this formula yet for part C because I don't know mu k. I didn't give it to you, so you're going to use that for part D, by the way. But here's the deal with part C. You do ma, so the mass is 65 kilograms, times acceleration equals tx, which you're going to know is t times cosine theta, minus fk. And your job is to solve for fk. Now here's the deal.
Isn't there no acceleration?
Good. Yes, you're paying attention. Awesome. Why?
Because it's constant velocity.
Thank you. Perfect. So that's what's going to be 0 straight up. And you already know what at t is. It's 160. You already know what cosine theta is. Cosine of 30 degrees, use your calculator there. You'll be at fk. Then in part D, so hold on a sec here. I'll sneak in part D. Then in part D, you're going to use this formula. Fk equals mu k times Fn. Fn you got from part B. Fk you got from part C. Now you can do mu k. So that's what your
What equation do we use for part D?
right here. Fk equals mu k equals times Fn. And the more I think about it now, maybe that's how we do the mystery object thing. Maybe I was really overcomplicating that. Yeah, I mean, maybe that was it. That's all I had to do. Yeah, I think we'll come back to mystery object one more, third time's a charm. But before we do that, let's put you guys in groups. So you guys are going to finish 1 and 2, the assessment part of the lab. I've given you all the things you need. Hope you took good notes, and I'll put you guys in groups of 3. So just get all of your answers there. I'm going to work it out too, just to make sure our answers line up. And I'll give you guys 15 minutes. I think that should be fine. Then we're going to do a little lesson on tension after that. So let me clear the screen. Stop sharing. Stop recording this.